This video will show you how to set up a point source Plume in version 6.2. So you're going to start with chemical species transport, transport of dilute species. Put that physics in, and then I'm going to delete that because I already put it in. You can see it up there. You're going to want to put in the convection, check that off. And the dependent variable is lowercase c. Let's take a look at some more aspects of the setup. So we've got two global parameters here, and here are the variables: the diffusivity, dispersivity, the Peclet number, and the cell Peclet number. And the geometry, there's a rectangle of this dimension, and then the x and y offset of the corners is set up so that when I put the source in as a circle, I can put the circle in at 0, 0. So there's the rectangular domain, and this is the source. The radius is the global parameter LDIAM, and you can see it right in there. It's at 0, 0, and the LDIAM is a parameter right there. Okay, so that's the geometry. Pretty simple. There'll be a source in that circle, and there'll be flow from left to right. So here's how to set up the physics. We check off convection, and then we're going to need to specify the velocity field. And in this case, we're just going to have uniform velocity of magnitude x VEL. So that'll flow from left to right. We don't have to solve for any physics. The fusion constant or dispersion constant is shown there. It's the sum of the dispersion and the molecular diffusion. And then these are just defaults. The concentration initially is going to be 0 in the outside domain, and the concentration along the edge there is held at 0. The outflow is specified on all four boundaries. So mass can leave by convection or advection across all four boundaries, and then the initial concentration inside of the domain is equal to 1. That's what the mesh looks like. Here are the specs on the mesh. With these advection problems, if you have the mesh be too coarse, you can run into numerical difficulties. So this mesh should work all right for our purposes here, unless the Peclet number gets to be too large, and then we may need to revisit that and make the mesh smaller. So here's the specs on the study. Going to display the results as we go. So we'll run it. Flow from left to right gives us a plume from that point source, and you can see the dispersion spreading it out. Runs pretty quickly. And then here are the graphics showing the results. I've got a cut line at x equals 200 or 300. And so let's just change that. And it's a vertical cut line to show the profile, and there's some cut points. This is the color flood of concentration, and then I put in a contour at 0.01. That's that white contour line. That's really meant to be the limit of the plume. If you put in 0, it doesn't show up because everything has a little bit of mass in it. So we have to give it a small value, and that shows you the limit of the plume. Here's the cross-section perpendicular to the flow. This is at that cut line. You can see the shape of it. It's right about in there. And then this is the cell Peclet number. If this gets to be too large, then that can be a source of numerical problems. The cell Peclet number I calculate right there, where H is the dimension of the mesh element. And then this is the breakthrough curve at these 3 points that we defined as cut points. And they are located right there. So you can see the first one to arrive is the largest concentration, and then the concentration decreases and arrives later as we move to points that are further downstream. Here's the Peclet number calculated as a global variable. I also am displaying the Peclet number in the title of this 2D plot. So you can see there's the setup. That eval t and eval pe evaluates the time and the Peclet number and plots them up there in the title. So that's another way to take a look at the Peclet number and the time as you go.